Right, we are looking at sequences, and there are three main kinds of sequences. We've got linear, quadratic, and geometric. And we're going to go through all three and then do a couple of kind of exam-style questions at the end. So let's look at linear first. Linear is the nicest kind of sequence. It's the simplest one to solve, so hopefully it won't be too bad. So just to take a step back, we use n to talk about the position of each number in my sequence. So these actual numbers are the numbers we're interested in, right? This is my actual sequence. We just label them by their position in the sequence. So 11 is my fourth number in the sequence, or the fourth term in the sequence, and so we say n equals 4 for 11, and so on. So the first thing we're going to do when we're trying to work out a kind of a general expression or a general rule to define what's going on here is we look at the difference between the numbers. And so the difference between the first and second numbers is we add on 3, right? 2 plus 3 is 5. And with 5 and 8, we add on 3. 8 and 11, again, we add on 3. And we can see we've got a general pattern forming here, right? We add on 3 every time. And so if we want to have an initial guess of the expression that would represent these numbers, can we think of anything that goes up in jumps of 3? Well, we know, hopefully from years and years ago, our 3 times tables goes up in jumps of 3. And so my first guess at a representation for this sequence is going to be my 3 times tables. Well, how do we represent that? Well, my 3 times tables is just I take 1 and I times it by 3, I get 3. I take 2, I times it by 3, and I get 6. I take 3, I times it by 3, and I get 9, and so on. This is my 3 times table. So every time I want to work out my next number in my sequence, I look at what the value of n is, the position of that number, and I times it by 3. And so what I'm doing is 3n. And we can say this is like our first guess, basically, our first guess at what the sequence could be. Sorry, what the expression for the sequence could be. And we're not far off, are we? If we look at each term in the sequence, we've for our first term we've got 3, we want 2. For our second term we've got 6, we want 5. We've got 9, but we want 8. We can see we basically need to subtract 1 from every single term in the sequence. And so if I just extend this table down a bit, we're going to have a go at a second, better informed guess now. And so we're going to say we're going to stick with the initial guess of 3n, but we're actually before we actually do anything, we're going to subtract 1 from it, and then we're going to work it out. And so rather than 3, we're going to have 2. Rather than 6, we're going to have 5. Rather than 9, we're going to have 8, and so on. And what we can see is we're starting to get our sequence come through, right? We've got 2 and we've got 2, we've got 5 and 5, we've got 8 and 8, 11 and 11, 14 and 14. And so I know that this is going to be the expression for my sequence. Right, let's go on to quadratic sequences. These are slightly trickier. And again, we start off with the same general principle. So we look at the difference between each term. So we've got plus 3 here, 4 up to 9 in this case is going to be plus 5, 9 to 16 is plus 7, and you can probably guess what the pattern is. 16 to 25 is plus 9. And now, the extra thing we do is we look at the difference between the differences. And what we can see is that is now a constant value, plus 2, plus 2, plus 2. Well, if we take a step back for a second, we know what these numbers are. We know the rule already for this, because these are just square numbers, right? All I'm doing is I'm taking the value of n and I'm squaring it. I'm taking the value of 2, for example, I'm squaring it to get 4. And then I'm not really timesing it by anything, I'm just timesing it by 1. I'm not changing the value after I've squared it. And so what I do is I'm taking n, I'm squaring it, and I'm timesing it by 1. And the reason I'm putting 1 there is because that's how these two different things are related, right? We know that our difference between the differences is 2, and the general rule is we take the difference between the differences, we divide it by 2, and that then gives us the number in front of x squared. And that's the rule that we use to solve quadratic sequences. Right, moving on to geometric next. Geometric is quite a bit different from linear and quadratic. I think the easiest way to understand this is we've basically got a starting number, and then all other subsequent numbers are kind of calculated from that initial starting number. Geometric just means we've got a common scale factor between the numbers. And we can see here, right, we've got 2, 6, 18, 54. So we can see every single time we calculate the next number in the sequence, we're actually timesing the previous number by 3 every single time. Well, if we were to lay this out in a slightly different way, it hopefully start to make sense. How we're going to get a rule to actually, or an expression to define this sequence. So I've got my starting number, which is 2. So I take my starting number of 2. To get 6, to get the second number in my sequence, I take my starting number and I times it by 3. To get the next number, to get the third number in my sequence, I take the previous number, in this case it's 6, and again I times it by 3. I'm going to write 6, instead of writing just 6, I'm going to write 6 as 2 times 3. So I take 6, which is 2 times 3, and I times it by 3. And that gives me the third number in my sequence. The fourth number in my sequence, to get 54, I take 18, or I take 2 times 3 times 3, and I times it by 3. And so, therefore, I take 18, times it by 3, and that gives me 54. And I can keep doing that, right? But again, we can see a pattern emerging here. Well, how can I write 3 times 3 times 3? 3 times 3 times 3 is just 3 to the power of 3. 3 times 3 is just 3 squared, and 3 is obviously just kind of 3 to the 1. We could think of that as 3 to the 1. And so whenever I want to work out the next term in my sequence, however many jumps ahead I want to go, I take my starting number and I times it by the scale factor, which in this case is 3. So I take my starting number, I times it by the scale factor, and I put that scale factor to the power of however many jumps I need to make to get to that term that I'm interested in working out. Right, so if I wanted to find the fifth term, all I need to do is I take my starting number and I times it by 3 to the power of however many jumps I need to make. Well, I need to make 1, 2, 3, 4 jumps in total, so that'll be 3 to the power of 4. And we can test that out, right? 2 times 3 to the 4, well, 3 to the 4 is going to be 9 times 9, 81, and then 81 times 2 gives me that 162. So it's start number times the scale factor to the power of jumps. The power of jumps. Hopefully that makes sense. Right, let's go on to look at a couple of kind of exam-style questions just to finish off this topic. So first of all, we're going to look at arithmetic sequences. I don't know if I have left some random scribbles on here before. I'll get rid of those. So we've got a very similar thing we had on the previous page, right? We've got a set of numbers and we've got hopefully a common difference between the two. And if we look at what's happening between 6 and 11, we're adding on 5. Between 11 and 16, again, we're adding on 5. And we start to see that pattern emerging, right? Well, what goes up in jumps of 5? We know that our first guess is going to be our 5 times tables. So 1, 2, 3, 4, 5. If I look at my my sequence here, my first guess is my 5 times tables, right? It's 5n. So 5n, 5 times 1 is 5, 5 times 2 is going to be 10, 5 times 3 is 15. It's literally my 5 times tables, no more complicated than that. And where are we up to now? So how's our first guess performing? Well, we've got 5 for our first term, but we want 6. We've got 10 for our first term, but we want 11. We've got 15, but we want 16. And so again, I can see that I need to add on 1 to every single term. And so that then gives me 6, 11, 16, 21, and so on. And so because I've now kind of recreated this sequence, I know that my my expression is going to be 5n plus 1, and that's going to be my answer. Right, let's look at quadratic sequences next. So if we were to look at this one, this is a slightly differently laid out question. So for this one, we're given the expression, and we want to actually work out the 10th term of the sequence. Well, I know the 10th term of the sequence, n is going to be 10, right? I know for the 10th term, n equals 10. That's what n does, right? It tells us the position of the term in the sequence. And so what I do is I take 10 and I shove it into this expression. So I put 10 into here and into here. So what we end up with is 2 times 10 squared plus 4 times 10 minus 1. Well, 10 squared is 100 times 2, it's going to be 200. 4 times 10 is 40, and minus 1. So we get 2, 3, 9 as our answer. Right, finally, we'll go on to geometric sequences. So we're given our start number, which in this case is going to be 100. And we're told that it doubles every 3 hours, and we're interested in how many bacteria we'll have after 24 hours. So how many jumps is that going to be? Well, how many times does 3 go into 24? It goes into 24 8 times. And so we're going to have 8 jumps. And so just like we did on the previous page, I've got my start number, which is 100, times my scale factor. Well, I know it doubles every 3 hours. So my scale factor is going to be 2. And the power is going to be 8, right? That's how many jumps we've got. Well, 2 times 10 to the 8 is 256. So it's going to be 100 times 256, which gives me 25600. And that's my answer. And that is the end of sequences.